Greetings, my friends. I have something fun for you today. I am occasionally given old electronic or electrical devices to go over and make sure that they're safe. Somebody will find it in a thrift store or in a garage, and they want me to take a look at it and see if it is still operable or if I can fix it up or restore it or what have you. In this case, I was given this one. It is a metronome, which is, of course, a device for providing a synchronized beat or tempo for musicians. Metronomes have been around for a very long time. You've seen them, I'm sure, with the pendulum that swings back and forth, and there's actually a ton of videos on YouTube where people use those mechanical metronomes with the swinging pendulum to show how synchronicity works, where they'll have tons of these things on a sliding plate and eventually they'll all end up working together. There are other kinds of metronomes, purely electronic ones that just make a digital beep noise using an internal clock, or one like this, which is an electromechanical metronome. This one is from the 1950s, I believe, but it's based on an older design from the 1930s, and it's really, really interesting. Now, when I first got it, I was like, okay, I'll just take a look at it and everything will be fine. I've already started, removed some of the parts, so we'll go ahead and do this. I'm going to turn it off, because this thing is running on mains current. I'm going to turn off my power supply and make sure that it is safe to do this. I removed the back earlier, so I had to remove some screws and so forth. So it's just kind of like held together because I wanted you to see it in operation before I went and took it apart. But this is really kind of cool. See, the first thing that I noticed when I opened this thing up was, hey, there's a vacuum tube in here. And I found that very interesting because I did not expect to find a tube-driven metronome. But this one is, like I said, it's an electromechanical metronome. The ticking noise is provided by this little thing right here. This is a solenoid or a relay, and the current is sent through here, and it taps against this piece of wood. I think it's balsa or some other thin wood, and it's kind of a cool thing. It just goes... It makes a tick noise whenever it's actuated. And so, that part was kind of like interesting. But this was the one that really kind of made me wonder, because at first glance I was like, why does it need a vacuum tube for a metronome? And what's this big transformer here? But a little bit of digging showed me this is not actually a vacuum tube. This is a kind of tube called a Thyratron. And Thyratrons are actually really interesting. A Thyratron is a form of tube called a gas discharge tube. Now, rather than just, I can pull this thing out and show it to you, but honestly, it's not going to give you much detail if I was to try and point at the various things in there. So instead, I created a little diagram, and we'll just take a look at that diagram, and I'll discuss what a Thyratron is, and what it does, and why it's kind of cool. So here's a diagram of a Thyratron. This is actually the same symbol, or very similar to what you would see in a diagram of a circuit involving a Thyratron. And the first thing to note is that there's the big black circle right here. That represents the the glass envelope, or what you would call the tube. The black dot tells us that it's got gas in it. So in this case, the Thyratrons are a form of a gas discharge device. And so they rely on a principle that the gas inside is non-conductive until it has been ionized, which is a term that means that enough energy has been put into it in the form of electricity or heat or some other kind of energy, usually electricity or heat, that it becomes ionized, which essentially means that its electrons are much more mobile and much more free to move. And when electrons are free to move, they can become charge carriers, and that means that it can conduct current. And in that state, it will begin conducting current, and it will at that point be called a plasma, and is a very effective conductor of electrical current. A gas discharge device that almost all of us are familiar with is one of these. This is called a neon lamp. This is just a little neon tube, and if you look very closely, you can see that it's got two electrodes in it separated by nothing, right? There's just nothing in between them. Inside the tube is a small amount of neon. So when a voltage is applied to these two electrodes, nothing happens because there's a big old gap there until the voltage between these two electrodes is large enough that the voltage breaks down the resistance between the two electrodes, and then it ionizes the gas. That's called striking. The tube strikes, and then it begins to glow, and it begins to conduct current. So that's a very simple form of gas discharge device. But Thyratrons are a little bit more, they're a little different. They're a little bit more sophisticated, and they're pretty cool. So the way a Thyratron works, it really works on the same principle as a neon bulb or any other gas discharge device. But instead of simply relying on the voltage difference between the two electrodes, it adds a control called the grid or the control grid. Now, the first thing to understand about how tube systems work is you have to have a heater. Okay, the heater is powered by a separate set of current, in this case 6.3 volts AC, which is what that transformer was for, and I'll show you again when we bring this thing back into the camera screen. And that heats up the cathode. The cathode gets hot and begins to emit electrons in a small cloud, but they basically hang around the cathode and they don't go anywhere. They don't allow current to conduct between the cathode and the anode because they're all hanging around the cathode. And then the grid will be at first will be negatively charged, and that will keep and push the electrons back away from the grid, preventing electrons from moving toward the anode. But then as soon as the grid becomes positive enough relative to the cathode, then all of a sudden the electrons are like, hey, we want to go this way, and they begin moving towards the grid, and they flow through the grid, and then they begin conducting through to the anode, at which point the tube is said to have fired or struck. It strikes, and then current can flow from the cathode to the anode. Now, it's also important to note that current will never flow from the anode to the cathode. It's always one way. So this tube acts as a form of a diode, and it only allows current to go in one direction. So, but what happens is the way this grid works, this is called the control grid or just the grid. If the grid is at the same potential as the cathode or is negative relative to the cathode, then it repels electrons away and doesn't allow them to move towards the cathode. But as soon as the grid is positive enough relative to the cathode, which the cathode should be negative, then all of a sudden it goes boom, and electrons begin flowing and carry current from negative to positive. The electrons flow from negative to positive from the cathode to the anode. And the cool part about a Thyratron is at this point, then the control grid, you can do whatever you want with it. It doesn't really matter what the control grid does at this point, because now the gas in between the cathode and the anode is said to be ionized. It's become a plasma, and it's now its own charge carrier, and it will carry electronic current. It'll carry current from the cathode to the anode as long as the voltage difference now between the cathode and the anode remains high. As soon as the voltage difference between the cathode and the anode drops, or they become close enough, then the tube stops conducting, and it won't start conducting until the grid comes on again. So that basically makes this into a sort of like a locking switch. Current doesn't flow until you apply a voltage to the grid, then the current flows, and it keeps flowing until you turn off the power between the cathode and the anode, and then you can't restart it again until the grid goes positive again. So it's sort of like a switch that you can press, and it stays on until whatever is going through the switch turns off. So let's bring this thing back in just a second, and let's go over the circuit, and we'll look at it we'll look at the device, and we will show you what this thing does with a regular, I'll show you the full schematic of the device, and then we'll show you how it operates and go over its principle of operation. And then a little bit later, I'll even throw it on an oscilloscope and we can watch it. So stay tuned. Okay, so this is a schematic I came up with by reverse engineering the metronome. And the first thing you'll probably note is that the Thyratron symbol is right here, and it's really, really similar, almost identical to the one that I showed you before, with one difference. This one doesn't have the screen grid here, and the screen grid essentially just provides more control and makes the Thyratron more stable, and isn't really important for what we're talking about here because its actual principle of operation doesn't change, so we'll just ignore that for the time being. But as you can see, we've got the cathode and the anode, and then there's the neon lamp here, which is the one on the front of it that flashes, a couple of capacitors, a potentiometer, and remember that transformer I showed you before? Well, the transformer that's right here. Well, that's this, and that transformer, it connects to the heater, and that's what provides the heater power for the Thyratron, and that's its only purpose. So in this circuit, we'll take a look at it here. In this circuit, the Thyratron is acting as something called a rectifier, and the rectifier is a device that turns alternating current into direct current, or in more precise terms, it takes alternating current and only allows current to flow in one direction, which is usually DC, but can be like pulsed DC or something like that. But this one is a little bit, it's being used a little bit differently, and I think it's really, really interesting. So when we close the switch right here, well, it's plugged in and it's not right now, we close this switch. So when that switch is closed, the voltage, or excuse me, the 60 hertz AC coming in from the power from the wall is immediately applied to the circuit. Now, the first thing that happens, I'm going to set this thing aside because it might be a little bit easier to look at it on the circuit diagram, is that you'll have 60 hertz alternating current coming in, and the anode will begin swinging positive and negative at 60 cycles per second, and the cathode will be essentially through this relay and this resistor be at a much lower potential than the anode when the anode is high, and reverse when the anode is not, as you can see. So as the voltage swings positive on the anode, it's also being sent through the grid, through this potentiometer, to the control grid. Okay, so this is acting as a voltage divider, and that means that the cathode will be at a lower potential than the grid at some point, and that just depends on what the knob here is set to. And at some point, the cathode will be lower relative to the grid, or you could say the grid will be high relative to the cathode. And that, as the voltage on the anode goes high, the voltage on the grid also goes higher, while the cathode is being pulled lower. When the voltage on the grid is high enough relative to the cathode, the tube goes into conduction mode, and that means that the gas inside it becomes ionized and allows electrons to flow from cathode to anode, which essentially means current starts flowing from one side of the circuit to the other. As the there's extremely low resistance initially between the cathode and the other side of the circuit, right here to here, because as this capacitor right here is empty at the beginning of this process, and so that sees it as extremely low resistance, and you get a huge spike of current flowing that charges this capacitor extremely quickly. So when the Thyratron fires, this capacitor C1 begins charging extremely quickly, and my measurements showed it to be about 300 to 400 microseconds. That's really fast. So as it charges up, though, a few things happen really, really fast. Since current is flowing to charge capacitor 1, that means that this solenoid right here, which I've just represented as a little relay, that fires, and that's what makes that tick noise. The plunger extends, and it stays extended as long as current is flowing through here, and that makes that tick noise, and then it sticks out, but it's very, very quick, as you'll see in a moment. So this that solenoid is actuated by the current flowing, and that causes it to strike the wood surface, making that tick sound. And it stays in that position as long as there's current flowing in the wire. So that means that the voltage here between this side and this side of the neon lamp, well, that climbs. And at some point, the voltage difference between this part of the neon lamp and this side of the neon lamp is high enough that the neon lamp conducts. And when it begins conducting, it's said to strike, it turns on, flashes, and begins charging C2. All right. So, but at the same time, charge is building up on here. And as that charge builds up, that means that the cathode is no longer seeing the same high current path between here, because once a capacitor is fully charged, it stops passing current. It never really passed current in the sense that you might be thinking, but the current flow of the cathode is seeing drops. And that means that the cathode is going to be going higher voltage-wise relative to the anode. And as the capacitor continues to charge, the voltage difference between the anode and the cathode gets lower and lower. And as we discussed before, then the tube will quench and stop conducting. So when that potential difference between cathode and anode is high enough, then the tube stops conducting. That now leaves this part of the circuit essentially isolated. The solenoid retracts because there's no longer current flowing here. And then capacitor 1 will begin discharging through this resistor. Capacitor 2 will begin discharging through this resistor. And at the same time that the capacitor 1 went high enough to drive the cathode high enough to quench the Thyratron tube, it's also changing the potential difference between here and here. And that means that the neon lamp stops conducting. So now capacitor 1 discharges through this resistor, capacitor 2 discharges through this resistor, and the cycle begins again. And the cathode's potential, as this resistor discharges, it pulls this leg of it down through this wire here, and as it pulls down and down and down, eventually it will be a low enough to be far enough of a difference between the cathode and the control grid that conduction can begin again. And the point that happens is dependent on this voltage divider. So depending on how this is adjusted determines when in the AC cycle the control grid is high enough relative to the cathode to fire the Thyratron. And I think that's really interesting because the cool part about this is that all of this happens in the space of just a few hundred microseconds. So it goes and the solenoid clicks, this thing conducts, these things charge and discharge, and then the bulk of the operational cycle of this entire metronome is these capacitors slowly discharging through these resistors until the value on the capacitor drops far enough for this resistor here to bring the control grid high enough for the Thyratron to fire again. Very, very cool. So we can see here, if we look at the bottom of this thing, this is the Thyratron tube socket. There's the variable resistor. This is C1, this is C2. Those are those 910K resistors. That's the 6.2K. There's a couple of others over here. And there's the switch. There's the transformer that drives the heater for the Thyratron, and that's the solenoid. Now, what I'm going to do is I'm going to set this thing down for a moment, and I'm going to put a couple of leads on it, and we're going to look at it with an oscilloscope, so we can actually kind of like observe this thing in operation, and you can get a sense of what it's actually doing, because just describing it is sort of, might be interesting, but I think you'll find it much more interesting to see it in action. Now, once I'm done with all of that, I'm actually going to be taking these capacitors and all these resistors out, and I'm replacing them because these capacitors should not be considered safe. These things are like 50 years old, and I would not want to rely on them long term. So I'm going to take these out, and I am going to actually gut them and replace them with new capacitors. I've got some here somewhere. Here they are. That will fit inside those cases and look like the old ones. And I'll show you how I do that in a separate video. That'll be kind of fun. But hopefully when all is said and done, this thing will work just like it was brand new, just like it came off of the factory, but with brand new resistors and capacitors, so it'll last another 50 years. So stay tuned, and we'll be right back with this thing up on an oscilloscope. All right, my friends, we're back. I have connected the metronome to an oscilloscope, and we're going to take a look at some of its characteristics in operation. However, before we go any further, I want to talk a little bit about safety. This metronome is intended to work on house current, AC mains. You plug it into a regular wall socket and it works. That is not something that you should be blithely just connecting to an oscilloscope unless you have an idea of what you're doing and have the right equipment. In my case, I am using high voltage differential probes. I have 2 of them. I have also placed the metronome itself on an isolation transformer to completely isolate it from my house current, and I have in turn placed the isolation transformer on a variac so that I can vary the amount of current going to the isolation transformer. Even with all of that, if I'm not careful, I can shock myself. There are lethal voltages present here, so I am going to be careful, and I'm going to tell you, don't try this at home unless you know what you're doing. It can be fatal. All right, so that said, let's take a look at what we've got here. I have the first probe here connected across C1 over there. All right, and so C1 is the first first capacitor in the circuit that is charging every time the Thyratron fires. And we can see here I've set these cursors to show me the amount of time it takes to charge this thing. I didn't do all the math or anything like that, but it's getting to the bulk of its charge in 3.76 milliseconds, or about 376 microseconds. That is really fast. And what that's telling me is that this thing is charging more quickly than you would think initially if you were just to look at the circuit. Now I'm going to turn on the second trace here, and this shows us the AC of the house current, or in this case the electricity coming out of the isolation transformer. But essentially this is the main power supply signal to the entire device. And as you can see, the capacitor gets to nearly a full charge as the AC current is dropping, and in less than a fifth of one cycle. So this thing is charging extraordinarily quickly. And as you can also see, it begins to conduct just as the AC current gets to the top of its voltage, which implies that the Thyratron isn't firing until it's at a pretty high voltage, or at the peak of the AC voltage. That's when the Thyratron fires and this thing begins to conduct. And if I'm going to turn off the cursors here, and I'm going to change the time scale so that we can actually see how quickly it's... Come on. It's giving me some... I'm going to turn up the frequency on the metronome so that we can actually see what it's doing here more easily. It basically just wasn't getting enough data. There we go. So each of these is one discharge and recharge cycle, but as you can see, that is happening over the course of many cycles of AC. So if we were to count these, it looks to be about 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 or 12, maybe 15 AC cycles for every one of these. And of course, if I change this frequency, it'll be different. But the point is that the metronome is doing all of its work within one AC cycle, and it begins discharging before the cycle switches back to or very, very rapidly. And so almost all of the work of the metronome, the capacitor charging and discharging, and or beginning to discharge, and the AC current swinging happens really, really quickly. Now I'm going to pause the video again, and then I'm going to hook it up to a couple of different points, and we'll observe some other characteristics of the circuit to give you more insight into what it's doing. Okay, and we're back. And this time I have set it up so that the yellow trace is on the capacitor 1 charge time, and the purple, I guess it comes across as blue on your screen, trace shows the cathode potential. So what we can see is that the cathode goes high, and then there's this strange gap, and then it begins charging. And why do we have this gap? Well, let's take a look here. I'm going to make another quick adjustment. Before I do, I'm just going to point out, you can see that this thing goes high and then has this ringing sort of thing. And then as the capacitor charges, then this thing quickly falls off, and they will rapidly come together as the cathode potential drops. And then when the cathode potential drops far enough, it spikes up again. And that's what's causing the metronome, or the Thyratron, to refire. And so what I'm curious about now, or what I want to show you now, is why doesn't the capacitor start charging instantaneously with the firing of the Thyratron, represented by this line going high? And I'll show you that in just a moment. Okay, and we're back one more time, and now I've got this thing hooked up so that the yellow curve here is showing the capacitor charge, capacitor 1, and the second curve here is now showing the charge time through the inductor, which in this case drives the solenoid that makes that ticking noise that you're hearing. And the reason that we were seeing a lag between the time that the current becomes available when the Thyratron fires and begins charging and when the capacitor begins charging is because inductors will take a moment to reach their full potential. Essentially, the voltage is going up on the inductor, and as it goes up, it creates a magnetic field, and that magnetic field is driving the ticking noise that you hear by pushing a plunger into the piece of wood. But while that is happening, no voltage is actually flowing out of the inductor because it's basically filling, it's building a magnetic field. And I'm oversimplifying things here, but essentially it's building a magnetic field, and then until it gets to a certain point, then no voltage is available for the capacitor. But as soon as that voltage gets to a certain point on the inductor, then it begins allowing voltage through, and it begins to charge the capacitor. Now here's something else that's interesting. You can see that the voltage reaches a peak here, and it's moving around a little bit because the thing is in operation, but that peak where it begins discharging or where it begins dropping, that's when the Thyratron stops conducting. But you'll notice that the capacitor doesn't discharge. That's because the voltage as soon as the Thyratron quenches, the inductor is actually pushing some of the energy that it stored in its magnetic field back into the circuit. And that's what's causing the capacitor to continue to charge briefly, and then the inductor voltage drops and so forth. Fascinating piece of kit, I think, and really, really cool to look at. So that's about it for this thing. You've seen the thing in operation. For my next video, I'm going to show what it looks like after I've taken apart all the pieces and replaced all the capacitors and so forth, and then do a follow-up on it. But for now, I think that we have done enough, and this video has gotten long enough that I'm pretty sure that we've covered all the salient bits. But I thought it was really, really interesting that a circuit that is this simple, 6 resistors and a Thyratron and 2 capacitors and 1 neon bulb, and you've got yourself a really, really funky and really cool, fully operational metronome. Oh, one other thing that I didn't show you guys that I thought was really cool. This thing actually has a volume control, and the volume control is purely mechanical. It basically, this knob here determines how far away this piece here is from, it essentially pushes the plunger in and out, the solenoid further away from the wood to make more or less noise. And I think that's a really elegant design because it doesn't involve anything except a knurled screw. So there you have it, a Selmer Metronoma deconstructed, or at least reverse engineered, and now we've looked at it and now we understand what it's doing. And next I'm going to recap it and put new resistors in it and then put it all back together and give it back to the person who gave it to me to go over. So I hope you enjoyed this video, and if you liked it, let me know, and I look forward to the next one. Have a good day, my friends.